Good evening everyone, I am Mr. Ish. Thank you for joining me for this video. I have recently posted two videos on this arctan antiderivative where we've seen a bunch of integrals that when you integrate them, you go into this arctan antiderivative. And in this video we want to present a closure to that topic so that we can verify that indeed the procedures presented are correct. We can enhance our confidence with regards to this arctan antiderivative that we have been obtaining and seeing thus far. A good way of verifying that indeed your antiderivative is good is to think back to the fundamental theorem of calculus. You know, if you have a function and you integrate it, you end up with an antiderivative of that function. If you were to take this antiderivative and you were to take its derivative, you would end up with derivative of the antiderivative, and this derivative of that antiderivative will be equal to your original function, and that's what we're going to be looking at in this video via two examples. We will look at an easy example first and we'll follow this by slightly more complex one. You know, based on the video I presented, very quickly you should know your answer should be something like this. 1 over root 10 arctan x over root 10 plus c. And I presented a video on how you can actually come up with this arrangement. It involves a substitution. The u is equal to x over root 10. U is equal to x over root 10, and you can solve for x is equal to root 10 u. But from this part right here you can do du is equal to 1 over root 10 dx, and dx is equal to root 10 du, and you take it through the integration procedure. Root 10 du divided by 10 plus x whole square. X right here was equal to this, root 10 u whole square. When you solve this you get root 10 integral du over 10 plus 10 u square. You can isolate the 10. You get root 10 over here in the top and then 10 on the bottom. You have du over 1 plus u square. When you take this to completion you end up with your final answer, and you know that's posted right here at the very top, and we can just say 1 over root 10. By means of simplification you get 1 over root 10 arctan. You'll resubstitute back the u value, which was x over root 10 plus c. To actually verify that this indeed is good, and we know it's good, but to verify just take the derivative of this antiderivative. You'll take 1 over root 10 outside because it's a coefficient, and you'll do the derivative via the chain rule. If u is equal to arctan x over root 10, then function with regards to u is arctan u, and then du with respect to dx is what that value here is for u, which is x over root 10. And you can do the derivative of this, which is not too hard. 1 over root 10 stays out as it does. You can do the derivative of this, which is also 1 over root 10, and the derivative of this is 1 over 1 plus u square. You have to resubstitute what u over here is. U is equal to x over root 10. These two combine to just give you 1 over 10. That's not too hard. And then here you have 1 over 1 plus u square, which is x over root 10 square. We have 1 over 10, and then here we have 1 over 1 plus x square over 10. You have to do a common denominator right over here. We'll have this 1 over 10 sitting outside. Here we have 10 plus x square, and this is 1 over. All you gotta do is a reciprocal of this complex fraction over here. You'll have 1 over 10 times 10 over 10 plus x square. These cancel out. You get 1 over 10 plus x square, and you end up back to your original function. So we know our answer here, our antiderivative, is good. Next we just look at a slightly more complex example. We do the derivative of the antiderivative and we'll indeed have verified that our answer was indeed good. And that's just the crux of this video. For our video this will represent the last question because it's going to be a short video. We have the integral of dx divided by 5 plus 2x square. And you look over here, something of this form, a square plus bx square, where the numeral 2 is represented by this b. The b creates that complexity I was talking about in the previous video. You have to somehow look at this denominator and try to convert it into this form as you saw in that previous video. And the best way you can do that is by doing this type of technique I was showing you. Create a little box, and this box will represent an x. What you would put over here is what would help you accomplish that conversion. You definitely need to have a u here in the numerator, and you have to somehow be able to cancel that 2. You can do so with a root 2 because it will square. You have to be able to isolate a 5, but you can do that by putting a root 5 over here because everything here will square out. And you know, x is equal to root 5 u over root 2. Therefore, u must be equal to root 2 over root 5 x. du is equal to root 2 over root 5 dx, and dx is equal to root 5 over root 2 du. Now you can employ all of these items here in your conversion procedure. You have a root 5 divided by root 2 du over 5 plus 2 parentheses x square, which is a root 5 u over root 2 square. Alright, let's go to the next step from right over here. Root 5 over root 2 integral du. We can open up this part. 5 plus, actually we won't open it, but we'll square everything out. We'll have 5u square over 2. These 2's can cancel out. And now we'll come right over here. Root 5 over root 2 integral du. We can isolate the 5. 5 into 1 plus u square. Now we're seeing exactly over here what we wanted right here. Bring the 5 right out here. You'll have root 5 divided by 5 root 2 integral du over 1 plus u square. You can simplify all of this. Root 5 goes in 5 root 5 times. That root 5 will multiply with this root 2. You'll get root 10. 1 over root 10 integral. Well, let's take this to completion actually. 1 over root 10 arctan u. But what was u? Right over here. Arctan root 2 over root 5 x plus c. Well, we can present a better, more uniform answer because we have a root 5 here, root 10. We can rationalize this. Rationalize this by doing numerator rationalization. Root 2 times root 2 divided by root 5 times root 2. You know we have an x sitting here on the top. You'll have a 2x over root 10. And that will substitute right here in place of u. So your final answer, as you will see, will be 2x over root 10. So it's 1 over root 10 arctan 2x divided by root 10 plus c. So this right here represents our antiderivative of that integral. What we want to do is verify that this is true, so we have to do the derivative procedure of this. If you do the derivative procedure, we'll end up back to where we were. Okay, so here's our antiderivative. Let's do the derivative of this. We're going to bring 1 over root 10 out as a coefficient. Then we'll do derivative with respect to u because you have to do a chain rule. If u is equal to 2x divided by root 10, function with regards to u must be arctan u. Arctan u. Remember, arctan u is the same thing as saying inverse tan u. And then du with respect to dx is 2x over root 10. 1 over root 10 stays as 1 over root 10. You can do the derivative of this, which is just 2 over root 10. You know that. And the derivative of anything like this is 1 over 1 plus u squared. This 1 over 1 plus u squared, by substituting this 2x over root 10, is what will create the little bit of a algebra complexity over here. You have over here 2 over 10. 2 over 10. You open this up, 2 over 10, but it's the same thing as saying 1 over 5. 1 over 5. So all of this boils down to 1 over 5. And then here you have 1 over 1 plus u square, which is a 2x over root 10 square. We have to do all of this algebra now. You have this 1 over 5 sitting outside happily, and then you have 1 over 1 plus 4x square over 10. Common denominator. You have 1 over 5. Let's come over here. You'll have over 10. You'll have 10 plus 4x square, and you know all of this is under a 1. You can flip this around. You'll have 1 over 5 multiplying by 10 over 10 plus 4x square. Isolate from right here. I'm going to isolate by using 2. You'll have 5 plus 2x square. Now all we have to do is just a bunch of cancellations. This 2 goes in 10 5 times, and this 5 cancels out with this. So we're ending up with just 1 over 5 plus 2x square, which represented our original function. Alright, and then we're done. And we verified it. So remember, when all else fails and you're just unsure if your final antiderivative, which is the result of your integration procedure, if you are unsure that it is correct, just use the basics of the fundamental theorem of calculus, take the derivative of that antiderivative, and you should end up back to your original function. If you do so, then your answer was correct. And that's all I wanted to show you in this video with regards to these arctan antiderivatives. Thank you for watching. Have a good night.